In the real world, the behavior of gases only conform to the ideal gas equation at relatively high temperatures and low pressures. And what I wanted to show on this graph, and by the way, these PowerPoint notes are posted, all right? This is a graph that has pressure on the x-axis. What is this? What's that unit for the y-axis? What's that? Moles, all right? Because it's PVRT, and what they're doing is they're using those variables to calculate for a sample of 1 mole of gas, how would it deviate from ideal behavior? All right, so these are experimental values. All right, how does the pressure change? How does the volume change? Temperature is typically held constant, so R and T are kind of constant, but they are kind of seeing how that pressure and that volume change. All right? You all right? All right, so, and you can see that different gases are going to deviate from ideal behavior in different ways. Ideal behavior would have maintained that one line at 1 all the way across. All right, so real gases. Now let's take a minute and look at the same gas, okay, at different temperatures, changing the pressure, okay? And you can see again, if this were an ideal gas, it should stay here. Okay. And I think what this graph shows is that for higher temperatures, you deviate less from ideal than what's shown for like a lower temperature. Okay, so deviations from ideal behavior. We'll explain what these two pictures mean in just a moment. But we talked about the assumptions that we've made in the kinetic, oh no, hang on. Assumptions made in the kinetic molecular model that break down at these high pressures and low temperatures. And the two that we're going to look at specifically is that volume of the gas particles and those attractive forces between the gas molecules. So these are the two points of kinetic molecular theory that don't quite hold true for gases at high pressure, low temperature. All right, so deviations from ideal behavior. Generally speaking, these are just rules of thumb. Ooh, yeah. All right. Behavior is going to deviate at pressures higher than 10 atmospheres and at temperatures that are approaching the temperature where the gas is converted into a liquid. That's also known as the boiling point. When we talked about the behavior of those ideal gases, we talked about kinetic energy, correct? All right, kinetic energy proportional to the absolute temperature. Why does a substance change a phase from like gas to liquid as I decrease that temperature? What's going on? All right, so it's a kind of a balance between your intermolecular forces, your attractive forces between particles, and the kinetic energy represented by the temperature. As you decrease temperature, decrease kinetic energy, the intermolecular forces become more significant. Do the intermolecular forces ever change? Good, beautiful. Bunch of head shaking, no. No, the intermolecular forces are constant. It just depends on the kinetic energy. All right, and hopefully that all makes sense. All right. So the 2 points that we're going to specifically look at, and the reason why we deviate from ideal behavior, is that real gases actually have finite volume. When we're at low pressures, we have a huge amount of volume between those gas particles. Those gas particles then move around the entire container. And because there's so few particles to that volume, it's like they have the entire volume to move in. As the pressure increases, you cut down on the volume between the particles. Now those particles don't have all that room, okay? And the free volume decreases. What happens is that Pivnert equation, now that volume of the gas is bigger than that predicted by the ideal equation. All right, so the important part here is at lower pressure, particles very far apart. It's kind of like they have the whole volume to move in. High pressure, you're squishing them together, they start hitting into each other more often. All right, they don't have as much room to move, and their volume becomes significant. Okay, now let's look at the attractive forces. These come into play when the particles are close enough, such as when we're at high pressures, that the attractive forces actually lessen the impact of a given molecule against the wall of the container. And that's what this picture kind of shows. Normally, you would get a forceful collision between that sphere and the side of the wall, creating the pressure. So the pressure is actually due to the number of collisions and also how forceful they are. But if these surrounding particles have these attractive forces for that particle, it's kind of like they hold them back from hitting that side of the wall with the full force. So as a result, the pressure of the gas is going to be less than what's predicted by the ideal gas equation. So what we can do, and I wouldn't take notes on this slide, just give it a second. The next one I think is better. We're going to make corrections for non-ideal behavior to that Pivnert equation. And we're going to use what's called the van der Waals equation. All right, so here's the van der Waals equation. And there's kind of like two corrections that are made. Oops, sorry, hang on. Oh dear. I haven't used this in a while. This correction here corrects for the attractive forces. Okay. So this makes up for that decrease in pressure that we see in a real gas because of those attractive forces kind of holding back on the collisions with the container walls of the surrounding nearby particles. And then we have the other correction that accounts for the volume of the molecules themselves. Hopefully you know that N is, I don't know what I did there. Moles, right? V is volume, beautiful. And then there leaves that A and that B. The A and the B are dependent on the specific gas. All right? You have to memorize these? No. The answer to that's no. Just want to see if you were awake on a Friday mid-morning, right? All right? No, please don't. That's just silly. All right? A and B are experimentally determined for different gases. There are tables. All right, so let's work out a problem using the van der Waals equation. That's spelled wrong. Yep. Yeah, I don't know. Anyway, so I've got 1 mole of an ideal gas confined to 22.41 liters at 0.0 degrees Celsius. It would exert a pressure of 1 atmosphere. That's ideal behavior. Now we're going to use van der Waals equation and the constants in that table you just got to estimate the pressure exerted by 1 mole of chlorine gas in 22.41 liters at 0 degrees Celsius. All right. Guys, for most gas problems, assume ideal behavior. For most gas problems, you assume ideal behavior. When you are expected to use van der Waals equation, there will be something in the context of the problem that kind of tells you to. Okay, it's going to say assuming not, you can't assume ideal behavior, assume a real gas is there, apply van der Waals equation to the following situation. All right, so look for things in the context of the problem that highlights that you should be treating it as a real gas, not an ideal gas. So what I'm actually going to do is I'm going to use van der Waals equation, but I'm going to isolate it for pressure. All right, and I don't know if I'm going to be able to fit it in this space. Spit it. That's not what I meant to say. You know what I meant. All right, so anyway, I have P plus N squared times A over V squared times volume minus NB and that's equal to nRT. So if I want to isolate pressure, okay, I'm going to divide both sides by V minus NB, right? And then, so that's nRT. So this adjustment here, that n squared over a over v squared, I'm subtracting that because it is lowering that pressure, so it makes sense that that's like a minus sign, right, for the correction factor for the attractive forces. So let's go and plug in values. What I have, 1 mole? Did I have 1 mole? I had 1 mole. 1 mole times 0.0821 liter atmospheres, mole Kelvin. We were at 0 degrees, so 273 Kelvin over 22.41 liters minus 1 mole times B for chlorine is 0.0562. 0.0562, and the units are liters per mole. And then I have to subtract, I knew I was going to run out of room, 1 mole squared times A for chlorine, which is 6.49. 6.49. Gosh, liters squared atmospheres over moles squared. And that's divided by the 22.41 liters squared. When you do all that, you should get .989 atmospheres. So for chlorine at these conditions, is it far off of ideal behavior? No, because it's about 1 atmosphere, right? What's STP? 273 Kelvin and 1 atmosphere. All right, so it's not that far off.